The toxic liquid that drips from every cargo ship you've ever seen. Look at this. That orange liquid dripping down the side of a cargo ship. Most people assume it's paint or maybe rust, a natural side effect of a steel hull sitting in salt water. And to some extent, that's true. But those streaks are not just rust. They are a symptom, a chemical signal that something deeper and far more dangerous is happening inside the hull, inside the tanks, and inside the industry that moves 90% of everything you own. That liquid has a name, it has a chemical composition, and it tells a story that the shipping industry has spent decades trying to keep invisible. So what exactly is it? The easy answer is oxidation. Iron reacts with oxygen and water and becomes iron oxide. Rust. Simple chemistry you learned in school. Both explanations, rust and salt water, sound reasonable, and to some extent they're true, but they don't explain the real reason those streaks keep appearing, or why they reappear 6 months after a ship gets repainted, or why, in some cases, that liquid isn't rust at all. To understand what's really happening, you have to look at where ships actually live and what that environment does to steel at a chemical level. Seawater is not just water, it contains roughly 35 grams of dissolved salts per liter, primarily sodium chloride, magnesium sulfate, and potassium. And salt is a conductor, an electrolyte. When seawater touches steel, it doesn't just wet the surface, it creates an electrochemical cell, the same fundamental principle as a battery. The steel acts as both the anode and the cathode at different microscopic points across its surface. Electrons flow, metal ions dissolve, iron atoms physically leave the structure and become iron hydroxide, then iron oxide. That's the orange liquid. It is not paint, it is the hull itself dissolving. And that process is not slow. In open sea water, unprotected steel corrodes at a rate of 0.1 to 0.4 millimeters per year. That doesn't sound like much until you realize a standard cargo ship hull plate is between 14 and 25 millimeters thick, and the rate accelerates as the metal gets thinner, as the protective coatings fail, as micro cracks form. In the splash zone, the area of the hull that alternates between wet and dry with every passing wave, the corrosion rate can be 3 to 5 times higher than on the fully submerged section, because oxygen is constantly reintroduced every time the wave retreats, because salt crystallizes on the surface when it dries and redissolves when the next wave hits, because that cycle never stops for the entire service life of the ship. Not magic, just electrochemistry working exactly as physics demands. But that's only part of the story. The orange streaks on the outside are visible. What's happening on the inside is not. Every large cargo ship carries ballast water. When a ship unloads its cargo, it becomes too light, dangerously unstable. So it pumps seawater into internal tanks to rebalance. A large container ship can hold up to 20,000 cubic meters of ballast water. That's 20 million liters, sitting inside the hull, corroding the tank walls from the inside out, simultaneously with the ocean corroding them from the outside in. Ballast tanks are corrosive environments under attack from multiple directions at once. The outside of the tank wall is exposed to seawater. The inside is exposed to salt water that has absorbed oxygen, sediment, and biological material from whatever port it was collected in. The overhead deck plating is exposed to humid air that cycles between condensation and evaporation with every temperature change. That cycle, wet, dry, is the most destructive pattern a steel can experience. More destructive than continuous immersion. More destructive than continuous exposure to air. It is what causes a corroded tank to eventually crack, pit through, and leak. And when it leaks, the first visible sign is liquid appearing on the outside of the hull. Orange, slow, continuous. The EPA has documented what that liquid actually contains when it comes from corroded ballast tanks. Rust inhibitors, epoxy coating fragments, zinc and aluminum from sacrificial anodes, iron, copper, nickel, and heavy metals including arsenic, cadmium, chromium, lead, and selenium. Not paint, not simple rust. A cocktail of industrial compounds dripping directly into the sea. In every port, every crossing, on every ship you have ever seen from a harbor wall. Now, the key question, if corrosion is that destructive, what has the industry done to stop it? The answer, for decades, was paint, specifically anti-fouling paint applied to the underwater hull to prevent barnacles, algae, and marine organisms from attaching, because biofouling isn't just cosmetic. A hull encrusted with marine growth can reduce a ship's speed by up to 10% and increase fuel consumption by as much as 40%. In the 1960s, the industry found what seemed like a perfect solution: tributyl tin, TBT, an organotin compound that leached slowly out of the hull paint into the surrounding water, killing any organism that tried to attach. It worked brilliantly. It became the global industry standard within 2 decades. And then scientists started noticing something wrong. Oyster populations near busy ports were developing grotesque shell deformities. Female marine gastropods were growing male reproductive organs. Entire coastal ecosystems within harbor zones were being chemically disrupted. The EPA described TBT as extremely toxic to aquatic life and a known endocrine disrupting chemical. At concentrations as low as 1 nanogram per liter, 1 billionth of a gram per liter, it was causing irreversible reproductive damage in shellfish. The IMO banned TBT in 2003 with full enforcement by 2008. But here's what doesn't appear in press releases. TBT persists in marine sediments for decades. It is still being detected in port sediments worldwide. A 2021 study found TBT-based paints still being manufactured and sold in parts of the Caribbean and Central America, more than a decade after the global ban. But the toxic liquid is an only corrosion byproduct and paint leachate. There's another source, and it's arguably the most underreported environmental problem in global trade. The IMO estimates that between 3 and 5 billion tons of ballast water are transferred internationally every single year. That water is collected at the port of origin, in coastal shallows, and discharged at the destination port, sometimes on the other side of the planet. That water is not sterile. It contains bacteria, viruses, plant spores, larvae, plankton, and living organisms from the source ecosystem. When discharged in a different ocean, those organisms are released into an environment with no natural predators and no evolutionary resistance. The zebra mussel invasion of the Great Lakes, an ecological disaster costing billions in infrastructure damage, is traced directly to ballast water discharge from ships arriving from Eastern Europe, the European green crab spreading along the Pacific coast of North America, toxic dinoflagellate cysts causing harmful algal blooms in waters that had never experienced them before. The IMO adopted the Ballast Water Management Convention in 2004. Ships are now required to treat ballast water before discharge, but compliance is uneven, enforcement at sea is difficult, and the liquid discharging from cargo ships at anchor is still, in many cases, coastal water collected thousands of kilometers away, carrying biology that does not belong in the receiving ecosystem. And then there is the bilge. The bilge is the lowest structural point inside a ship's hull. By design, it is where everything leaks to: engine oil, hydraulic fluid, cooling water, fuel residue, cleaning solvent. Everything that escapes from the machinery above collects at the very bottom of the ship. Bilge water contains lubricants, greases, cleaning fluids, and heavy metals including arsenic, cadmium, chromium, lead, and selenium, several of which are classified as known or probable human carcinogens. Marpol Annex I requires ships to treat bilge water using a certified oily water separator before any discharge. The legal limit is 15 parts per million of oil content. But bilge dumping, the intentional discharge of untreated bilge water directly into the ocean, is documented, prosecuted, and persistent. Between 1993 and 2012, the U.S. Department of Justice prosecuted more than 60 criminal cases of deliberate bilge dumping. Individual fines have reached $10 million. In several cases, engineering officers were sentenced to prison. The reason it keeps happening is purely economic. Treating bilge water and offloading it at a licensed port facility costs time and money. Dumping it overboard at night in open water costs nothing if no one is watching. That dark, oily sheen you sometimes see trailing behind a vessel at sea, that is exactly what it is. Costs the global maritime industry $50 to $80 billion every year, a figure cited by NACE and referenced by Classification Society, ABS, in 2021. Globally, 5 metric tons of steel disintegrate every second. 40% of all steel produced worldwide exists solely to replace steel that has already corroded away. 90% of structural ship failures are attributed to corrosion as either the primary cause or a contributing factor. Engineers fight it with zinc sacrificial anodes bolted to the hull, blocks of metal that corrode preferentially in place of the surrounding steel. They also employ impressed current cathodic protection systems that send low-level electrical charge through the hull to interrupt the electrochemical reaction. They also apply multi-layer coating systems to freshly blasted bare metal in dry dock, to tolerances measured in microns. And still, 6 months later, the streaks come back, not because the engineering fails, because the sea never stops and the ships never rest. The next time you watch a cargo ship enter port and you see those orange streaks running down the hull, you're not looking at rust. You're looking at electrochemistry, at regulation failures, at decades of industrial decisions and their consequences, at the slow, continuous negotiation between a steel structure and an ocean that wants it back. And now I'm curious, do you know what happens to a cargo ship when it finally reaches the end of its life? Where it goes, what gets done to it, and what it releases into the environment when it does?